Hello everyone, welcome to this session. So, as we have seen in last session that given a topological space, you have a subcollection of topology. When you call that subcollection would be a basis. So just verbally speaking, when it would be a basis if you can write a free open set as union of some members of that subcollection. Right. And we have seen one small equivalent criteria to observe that when something is a basis of a topology or of a topological space. Like I promised you in last session, now we will begin with a set and we will consider some, very special kind of subcollection of subsets which will give us a topology, and that topology will have that subcollection as a basis. If you didn't get what I am saying now, that's what this lecture is for. Let me begin with a kind of sort of motivation. Given a set, say X, we can now define various topologies. Right? Many topologies. We have seen many examples, right? Sierpinski's kind of topology. We have seen cofinite space. We have seen co-countable topology. We have seen discrete topology, indiscrete topology, and various other kind of topologies. So you have many topologies. But let us say I give you a subcollection. So let us say script B contained in X, B contained in 2 to the power X. So what is 2 to the power X? Power set of X. So let me just correct it. So say beta is a subcollection, basically some collection of subsets, be some subcollection of subsets of X. I am interested in a difficult question. So the difficult question is, does there exist a topology tau on X such that the script B is also sitting inside tau? Means, see, this is very interesting. This is not something you should, think, what is this? See, what we are learning here is, if I have some kind of subsets of some particular space, for some particular subset, a set, we have some subsets. We are interested in, does there exist a topology in which those subsets would be open? Isn't it? It's a very difficult and beautiful question. So let us answer this question today. How we can tackle these kind of things. Okay, so let me begin with, you can say, a theorem. Okay, theorem. Let X be a set and script B be a collection of subsets of X, okay? Such that it has two properties, guys. Number one, for any small x in capital X, for any small x in capital X, there exists what? There exists a member of the script B. In script B, there is a member such that this x belongs to this bx. Okay, guys? Why I have written suffix x? Now you know the way I write. Okay. Another property. If b1 comma b2 belongs to script B, okay? And for any, so let me write for any here, okay? Rather than if. For any. For any two members of script B and for any point inside these two members, intersection, the intersection of these two members, there exists a third member. Of course, this third member depends upon B1, B2 and X. I'm not writing in suffix and all because it will, have too many things to write. But wherever, whatever is necessary, we may write. So, for any X in B1 intersection B2, there exists a B3 such that X belongs to B3 and this is contained in B1 intersection B2. Okay, guys? This is the second property. So, what is the first property? For every element of X, there is a member in this piece of script B, which will contain that point X. And second condition is, if you take two members of script B and a point, any point in that, there would be a third member which contains that point and which is precisely inside B1 intersection B2, the two members, right? So this kind of collection we are taking, okay? So let me now write. Then tau, what is tau? Let us see. So u sitting inside X such that, what property this u have? Such that for any X in U, there exists a member in script B such that X belongs to B suffix X, which is contained in U. So it is collection of all such subsets of X such that if you take any point in that subset, you will have a member in script B which will contain that point and will be inside your set U. So we are defining tau like this, okay? So then what is the claim? Tau is a topology on X. Okay guys, tau is a topology on X. And script B is a basis of X along with tau of this topological space. I hope the statement is clear. So you see, I am answering the above question. Does there exist a topology in which these sets will be open? You see, if I am claiming that something is basis, that this grid B is basis of tau, naturally grid B is contained in tau, right? That's what the definition of basis is. It should be inside tau, then something happens, right? So I hope you understand why I have answered above question. So if you have these conditions, then you can say that above kind of thing would be possible. So what I can name this theorem or this kind of concept which I have defined in this theorem, basis for some topology on X, right? Because you haven't started with a topological space here. You have started with a subcollection and you are constructing a topology ultimately for which this subcollection is a basis, right? With these two special properties. Okay, we will be looking into examples and all, so don't worry. So let us but first prove this theorem. See, sometimes it's better to see examples first and then concept, but sometimes it is very important to see the general concept first, then the examples. So let me begin. So let us have proof. So we have to show this is a topology. So what two things we have to show? Oh, three things. So let us show one by one. So note that phi belongs to tau. Why guys? This kind of argument we have done many times with this argument or logic. Why? What is the condition? If you have a set, if you take a point inside it, if phi doesn't have any point, na? So naturally that vacuously that condition would be true. So that is called vacuous logic. I have discussed it before also. Okay. Another thing. So claim X belongs to tau. Let us see why. So this is 1 and this is 2. So we will be using like by 1 by 2. Okay. Like that. So why X is in tau? What you have to check? You have to take a point, arbitrary point in X, and you have to produce a member containing that arbitrary point and which is contained inside X, right? Something like that. So see, so let X belongs to capital X be arbitrary. So what it means, guys? By first, what is gonna happen? So by first, there exists B suffix X in script B such that what will happen? Can you tell me? So such that you can stop the video and you can also prove it on your own. If you want to do it, it's a very good thing if you will prove it on your own. So such that X belongs to B suffix X, which is precisely contained inside X. That is the first property. So I will not be, going up again and again because I know what is 1 and what is 2. So it is advisable whenever you see these sessions or lectures, you do uh, make use of your pen or pencil because it is very important to write so that you can be, with the flow of lecture. Okay. So what is the definition of tau? So this implies that is what the definition of tau is. So for any point you should have in the set you should have this kind of thing what is happening here. So X belongs to tau. Number 2. So let say u v belongs to tau. What you have to show, guys? You have to show the intersection is there. So again, how you will start with? You will start with a point. So let x belongs to u intersection v be arbitrary and fix it, of course. Right? So what you have to do? First write the meaning of this, right? So this implies, now we have done many examples. So this implies x belongs to u and x belongs to v, right? Now, what are u and v? U comma v belongs to tau. Use the meaning of that. So this implies there exist, say, b suffix u and b suffix v in script b such that x belongs to b suffix u, which is contained in capital U again, and x belongs to b suffix v, which is contained in capital V, of course. That is by the definition of a set. Why? Because the topology is defined like that, the collection of all subsets which have this property for every point, right? Now, so club these two. What you want? You want something like intersection. So you have this thing. I think now you know what I'm gonna use. So by second, there exists B3. So what is my B1, B2? My B1 is V suffix U, my B2 is V suffix V, and there would be a third member. So just write it B. So there exists B in script B such that what will happen, guys? X belongs to B, which should be inside BU intersection BV, and this is inside U intersection V. If you want to write X here suffix, that is also fine, because ultimately this set also depends upon X, right? See, that's what we need to show, right? So just see these things. We have taken an arbitrary point. What we have to do? We have to produce a member of script B. Where it is? We have produced a member of script B such that X belongs to Bx, and finally this is contained in my set, right? So what this implies? This implies U intersection V is inside my topology tau. Oh, sorry, the subcollection tau. I haven't proved it that it is a topology. I'm still proving, right? Okay, good. I hope this is clear. Let us have third. So now let's take some arbitrary members inside tau. So let G alpha, alpha in capital lambda, be a subcollection inside tau. Basically, it is contained in tau. Okay, so what you have to show? To show union is there. Let us see how we can do this. Again, what you have to do, guys? You have to take a point. So let X belongs to union G alpha, alpha in capital lambda, be arbitrary. Guys, what does this mean? This means there exists a beta in capital lambda such that what happens? I hope you know this is just by the definition of union. We have used many times. Okay. Now, what is G beta? Where is G beta? So G beta belongs to tau. It means there exists a member B suffix X in script B such that what will happen? X belongs to B suffix X. This is contained in G beta by the definition of tau, right? So you see, where is G beta? G beta is contained in union of G alpha, because the individual would be contained in union of all, right? including that thing, right? So I hope this is clear. So this will imply union G alpha. Alpha in this belongs to tau. So what we have proved here, we have shown these three properties, the properties of topology, which we need to verify to claim something is topology. So this implies tau is a topology on X. Very nice. There is something more. If you don't remember, let me go a little bit up. Okay, good. We have proven that this is a topology, but we haven't shown that what we have to show extra, that this grid be precisely basis of this topology, what we have proved. So if this is basis, of course, basis is inside tau. It have to be inside tau, and you know the rest. I mean the green color, orange color, whatever I have written this motivation. So we will complete that question. Okay. So let us show that final thing. Now, clearly, script B is sitting inside tau. Show it if it is not clear. Fine, guys? Okay. Now, I need to show that this is a topology. Oh, sorry. B is basis of tau. So what I would be doing? I will be using the characterization which I have told you in last session. So for any u in tau and x in u, apply the definition that u is in tau. There would be b suffix x in script b such that x belongs to b suffix x, which is contained in u, right? See, what is this? So this precisely implies what? Script b is a basis of x along with tau, or of the topology tau on X, what tau we have defined here. So it is by definition only. The way we have defined topology, it would be automatically the basis. I hope you understand this beautiful concept. So like I mentioned you, for and of are two different things. I hope it is clear, right? For some topology, right? That some topology is precisely defined as here as this tau. Okay, I hope you understood this. So some people use the word generated also, topology generated by the basis script B, but no need here to use those terminologies because there is a bit fault, or you can say just the English is a very tricky language. So we do have sometimes we don't have precise logical grammatical arguments to say something. Sometimes in English that happens. Okay, so that's why I'm not going into those terminologies generated and all. So for now I think this is fine. Now let me give you an example. I mean, we will be seeing many examples, so let me give you first one. Okay, so this is known as Smirnov topology. Smirnov was a topologist. You can Google his name or her name. So I forgot the gender, sorry. So yeah, you can search Smirnov on Google and see the contributions by Smirnov in topology. So let us see what this is. Okay, so let X is equals to R. Okay, and B is equals to, say, this collection. So what is this? Again, open intervals in R union these kind of sets. If you take an open interval, remove this set from that open interval. So A, B in R. Okay. So what is the claim? The claim is, see the language properly. Claim. Script B is a basis of no for some topology on R which we call as, or which is known as, Smirnov topology. I hope you get the distinction now completely, for and of which I was talking in previous session. Okay, you see, so what you have to, and what is the sum topology? So basically I'm gonna use above theorem. I will verify these properties. Let me go again up. I will verify these 1 and 2, and then you know what kind of topology is there, right? So let us show that it's a basis. Just you have to show the property number 1 and property number 2. Okay? Shall we proceed? I think we can. Now, so let us show the first one. For any x in x, what is my x? R here. X belongs to x minus r, comma, x plus r. You can take some r and r bigger than 0, any r bigger than 0 in fact. This belongs to this, where x minus r to x plus r, this open interval is where? This is then script B, right? You see here the definition of script B. It is collection of all open intervals with some more, more sets. What kind of sets? A comma B minus 1 upon n, n in n. These kind of sets. I hope this is clear. So first property is satisfied. Now second, let B1 comma B2 belongs to script B. Now there would be naturally the cases. So case 1. Both are open intervals, okay? So B1 is some A1 B1 and B2 is some A2 B2. So now, guys, so we are interested in what? What is the second property? For every point in intersection, we have to produce something, right? Okay. So let us take, say, x in B1 intersection B2, be arbitrary. Guys, see, if the intersection is empty, we don't have to show anything, right? So, such that B1 intersection B2 is non-empty, because if B1 intersection B2 is empty, 2 is true vacuously, that vacuous argument again. So let us take these two kind of. Now this intersection is non-empty, so let us plot. Say you have, this is A1 B1, your intersection is non-empty, so your A2 has to be somewhere before B1, right? These are open intervals, note that. So what is the intersection? So intersection is basically A2 B1, right? Or there is another possibility, or you might have something like this. Say A2 is here, B2 is here, and say your A1 is here, right? This kind of possibility. So what would be the intersection? A1 intersection B2. Basically, and you can see if there are more cases, basically B1 intersection B2 is again what? An open interval. Open interval. That's what I wanted you guys to observe. So take B3 is equals to B1 intersection B2 only. So what you have? X belongs to B3, which is contained in B1 intersection B2. Why? Because it is precisely B1 intersection B2 only, right? So you see, in this case, this property is clear, right? Let us do the next one. Case 2. Say B1 is some open interval, say A1 B1, and B2 is say open interval A2 B2 minus this set. By the way, no, okay, no, I don't want to say anything because what I was gonna say, I think you will observe later on by yourself. Then B1 intersection B2. See, what would be B1 intersection B2? Can anyone tell me about this? So, what you have to do, of course, you cannot tell me, I'm teaching to a screen, but yeah, so try it. So, what would be this B1 intersection B2? So, it is something like this A1 B1. First of all, this thing A2 comma B2 minus this set. So, my question is this true? Because if this is true now, you will see we will be, done. Let us see if this is true. So take a point, okay? Let X belongs to green. This is green and other would be orange, okay? So this implies X belongs to A1 comma B1, this interval, and X belongs to A2 comma B2, but X is not equal to 1 upon n for any n in n. Right, guys? So what this implies? Just let us write it in a different way. So this implies X belongs to A1 comma B1 intersection A2 comma B2, but X is not in this, right? So what it implies, guys? X belongs to the orange one, right? X belongs to this set A1 B1 intersection A2 B2 minus this set 1 upon n and n. This implies X belongs to orange. I hope this color is orange. I am bad at when it comes to name of colors. So orange. Right? So green one is contained in orange. I hope you understood what whenever I'm saying green and orange, what it is. Okay, let us proceed the other side. So now let x belongs to orange. Orange one basically this side. So what it means? This implies x belongs to this thing. A1 B1 intersection A2 B2, but x is not equal to 1 upon n for every n and n. Very nice. So what it implies? Just write it separately. But x is not 1 upon n for every n and n, right? This implies this. What it means? This implies, now let us use the green color. X belongs to A1, B1. This set intersection with this set. Right, guys? So you see, uh, what is the form of B1 intersection B2? Again, a member like this, right? Because you know, intersection of two open interval is open interval only. We have seen above, right? So this implies, conclusion is B1 intersection B2 is of this form, some C comma D minus 1 upon n in n for some C comma D in R. Right, guys? Because again, the intersection, because of this equality, okay, where it is this equality. I hope, see, I'm just not saying any intuition or something. I'm proving each and everything for you guys because, like how I am doing now, you should be also able to do. You will find plenty of other example in books, the two books which I have told you. Maybe three I have told you: Simmons, Munkres, and Tej Bahadur Singh. So you can look to many examples in these textbooks, but you should know how to write each and every specific thing. That's why I'm doing, these things. Now, what would be the thing? Take B3 is equals to B1 intersection B2, and we are done. We are done. Now, what would be the next case, guys? Case 3 would be both are of different type. No, that we have done. Both are of other same type. So case 3. B1 is equals to A1 B1 minus 1 upon n in n, and B2 is equals to A2 B2 minus 1 upon n in n. Now what I want you guys to do is complete the argument for this case. Write each and every details what I am writing. So complete the arguments. Just mimic my way in the beginning or your own way, but the logic should be, perfectly clear. So you see, by above theorem, by above theorem, this grid B, what was it? The open intervals and the open intervals minus that set 1 upon n in n, A, B in R, is a basis for some topology on R. Now, if you know the basis, you know the topology, right? How to find all open sets, take the unions, right? Or these sets also. And of of course the empty set and everything. That's how you see we have defined the topology, right? So this was an example. Like I told you, whenever you have two topologies on a particular set, what you should always do? You should always compare them. So let me have that comparison also. I'm so sorry. So comparison of what? We have many topologies on R. Let me compare two. So let tau 1 be usual topology. You know what is usual topology? Real line on R. And tau 2 be Smirnov topology on R. Okay. So let us see the comparison. Note that tau 1 is contained, actually properly contained in tau 2. So tau 2 is strictly finer than tau 1. Let us see why. So let U belongs to tau 1 be any open set. You know that you can write U as union of open intervals, not some you know particularly here, these kind of, say, x minus r suffix x, x plus r suffix x. You know what are these r suffix x, these choices. I'm not repeating, I'm just directly writing here. Now, see, x minus r suffix x comma x plus r suffix x is also open in tau 2, right? For every x in U. Why? Because tau 2 is Smirnov topology. Its bases contain open intervals also. So that's why. So this implies U also belongs to, sorry, open, no, so I should write here, belongs to tau 2. Belongs to tau 2. Because Smirnov topology has open intervals as, basic sets. They are in bases. Okay. So U in where? Tau 2. Because tau 2 is a topology. So you see it is contained, but. So this implies tau 1 is contained in tau 2. Now, let us take this set. 0, comma 1, capital A is equals to 0, comma 1 minus 1 upon n and n. So note that A belongs to tau 2, but is it open in usual metric R? No, right? Show it. Why this is not open? I hope you guys can do that. Okay. So this can't be an open set. Or is this? Let us see. Let me think for a moment, because if this is, I need to, produce some other example. So let us see if this is in tau 1 or not. So what it is? What about its this set? This set is actually, you're removing 1 upon n. So I think I should produce, some different kind of example. But this should work according to me. But just a moment, huh? let us have like this. Say -1 to 1. Okay? Yeah, this is a good one. So let me tell you why A does not belong to tau 1. Because if you take 0, see 0 is in A, but any open interval around 0, say -r. Okay, this is not contained in A. Why? Because you are removing some points, right? These 1 upon n and all. So by Archimedean property, you can complete the argument. Archimedean property. What by Archimedean property? That there exists n in n such that 1 upon n belongs to -r to r, but 1 upon n does not belongs to A. So that's one. So show it. Okay. Why? This is just straightforward by Archimedean property. Why I'm not doing it? Because I know that you have done many examples like this playing with Archimedean property. So I have also done few before, and I will be doing few as far as I will continue. So no need of doing it here right now. So you see, the Smirnov topology has many more open sets than the usual one. It's the bigger one. So now you have more open sets, and later on you will see what is the advantage of open sets as far as this the sessions and course will go on. And I have given you motivation also. Right now what we are doing, we are studying structure. Now we will later on we will see when two structures are same. So slowly we will go to those things. But first few lectures is about understanding, topology, the structure properly. So we are understanding the structure first. What kind of structure? Topological structure. So let me conclude my session here. I hope you are doing well and take care. Thank you very much. Let's meet in another session. Thanks.